Hi everyone. In this class, I will explain problems involving steady-state conduction through a plane wall with uniform heat generation.
Now let us work out a numerical example. A plane wall with thermal conductivity 42 watts per meter Kelvin, 120 mm thick, generates heat at a uniform rate of 7.5 into 10 raised to 6 watts per meter cube. The two sides of the wall are maintained at 170 degrees centigrade and 140 degrees centigrade. Neglecting end effects, calculate temperature distribution across the plane wall, the position and magnitude of maximum temperature, the heat flow rate from each surface of the wall. So thermal conductivity of the material of the wall is given, the thickness is given, the rate of heat generation is 7.5 into 10 raised to 6 watts per meter cube, and the temperature on either side are 170 degrees centigrade and 140 degrees centigrade. You have to find out how the temperature distribution occurs across the plane wall, and position and magnitude of maximum temperature. So what distance this maximum temperature occurs, and also you have to find out the maximum temperature. The heat flow rate from each surface of the wall. So you need to find out the heat flow at the left end and right end of the wall, because heat transfer is varying with the x direction. Now the given data is tabulated here. Temperature T1 is 170 degrees centigrade. T2 temperature on the other end is 140 degrees centigrade. Thermal conductivity is 42 watts per meter Kelvin. The rate of heat generation is 7.5 into 10 raised to 6 watts per meter cube. Thickness of the wall is 120 mm, which is 0.12 meter. Now we know the temperature distribution in the wall is given by T plus Qx square by 2k is equal to C1x plus C2. This we are getting by double integration. After writing the governing equation for one-dimensional steady-state heat conduction through a plane wall with a uniform heat generation, you can integrate it. The governing equation is d square T by dx square plus Q by K is equal to 0, assuming that material is having constant thermal conductivity. Integrating that governing equation twice, you get the expression for T. So it's T plus Qx square by 2k is equal to C1x plus C2. So this is general equation for temperature. Now based on the situation, you have to solve for C1 and C2. Now let us start from the basic, and general case we derive substituting Ts T1 and x is 0 and Ts T2 and x is equal to L. And then later on we will substitute the temperatures and thickness of the wall. Now applying the boundary condition x is equal to 0, T is T1, you get T1 plus x is 0. Temperature is T1, x is 0, so x is 0, so you get C2 as T1. Now second boundary condition is x is L, T is T2. So substituting T as T2, then x is L, you get this expression. And also I substituted for C2 as T1, so you get T2 plus QL square by 2k is equal to C1L plus T1. So C1 is T2 minus T1 by L plus QL by 2k. This expression we already derived. But once again, as a part of this problem, I am deriving in the form of general equation and then substituting the values. Now substituting C1 and C2 in the expression for T, you get T plus Qx square by 2k is equal to C1 into x, C1 into x, so T2 minus T1 by L into x plus this into x, so QLx by 2k plus C2 is T1. So T is equal to, taking the Qx square by 2k to the right hand side, T is equal to minus Qx square by 2k plus T2 minus T1 into x by L plus QLx by 2k plus T1. Now we will take Qx by 2k, which is common in these two terms outside. So Qx by 2k if you take outside, you will get L, and Qx by 2k if you take outside, you get minus x. So Qx by 2k into L minus x plus T2 minus T1 into x by L plus T1. So this expression for temperature is a general case. Now let us substitute the given data. The heat flux is given, thermal conductivity is given, the thickness of the wall is given, all temperatures are given. Let us substitute that. So Q is 7.5 into 10 raised to 6 watts per meter cube, and thermal conductivity is given as 42 watts per meter Kelvin. and the thickness of the wall is 0.12 meter, and temperature T1 and T2 170 and 140, and this is the thickness of the wall, and this is T1. So substituting that and reducing, you will get an expression for temperature as T is equal to minus 89,285.714 x square plus 10,964.286 x plus 170. As you all know, this is an expression for parabola. So it is a parabolic variation. Temperature varies parabolically within the material. Now, as the temperature varies parabolically, as I shown here, there will be a peak somewhere at any distance location. You will have a peak. Now, to find out the peak, you already know the expression for temperature. A parabolic equation we got. At the peak, you will have slope 0. So, wherever the peak is occurring, the slope will be 0. You can differentiate this expression for temperature and equate that to 0. That will give the value of x at which this peak occurs. So, knowing that at the peak the slope is 0, you can differentiate the temperature equation which you obtained and equate to 0, which will give the value of x at which this peak occurs. And later, after getting x, you can substitute that value of x in the temperature equation to get the temperature at that location. Now, to find out the maximum temperature, equate the slope of a temperature curve to 0. Differentiate this, that will give dt by dx. So when you differentiate x square, when you differentiate, you get 2x. So 2 into this constant into x plus when you differentiate with respect to x, you will get 10,964.286 is equal to 0. So solving this, you get x is equal to 0.0614 meter. So from the left end 0.0614 meter away, you will get the peak point for the temperature. So temperature will be maximum at this location. Now this you can substitute, this value of x you can substitute. This is a location at which maximum temperature occurs, and this value you can substitute here, that will give the maximum temperature. So in the expression for temperature, you substitute x as 0.0614, which will give the maximum temperature. To find out the maximum temperature, substitute x as 0.0614 in the expression for temperature. You will get the maximum temperature as 506.603 degrees centigrade. This was your temperature expression which you have got in the previous slide. Substitute x as 0.0614 and solving for, you get temperature, maximum temperature as 506.603 degrees centigrade. We have to find out the heat flow rate on either side of the wall. We know the dt by dx. Once you know the slope, you can find out the rate of heat flow as minus Ka dt by dx. But taking unit area, minus K dt by dx at x is equal to 0. So this is important because based on x, the value of heat transfer is changing, because dt by dx depends on x. dt by dx is a function of x. So even q is going to be a function of x. So minus K dt by dx at x is equal to 0 is the heat transfer when x is equal to 0. Now substituting K is 42, dt by dx, and this expression dt by dx, you substitute x as 0, first term will be 0, you get 10,964.286. So you will get the heat transfer at the left end of the wall as 4,60,500.012 watts per meter square. Because it's for unit area we have calculated this, you can write it as watts per meter square. Dividing by 1000, you can write in kilowatts, 460.5 kilowatts per meter square. So this is the rate of heat flow at the left end of the wall. Now to find out the heat flow at the right end of the wall, once again you can apply the same equation, minus K dt by dx, but again A is taken as 1 for unit area. K dt by dx minus K dt by dx at x is equal to 0.12. So dt by dx we know, substitute x as 0.12 and K is 42. Substituting that, we get 70,39,499.964 watts per meter square. So if you divide by 1000, you will get 7,039.499 kilowatts per meter square. So this is the rate of heat flow at the right end. So you have seen that left end heat flow rate is less, and the right end it is more. It is increased from 460.5 kilowatts to 7039.499 kilowatts per meter square area. This is because of heat generated within the wall. So the rate of heat transfer is varying with respect to the distance. The heat transfer is continuously changing. As the heat is flowing through the wall, the rate of heat flow is also changing. Thank you for watching.